Hello, welcome to the video for Chapter 2, Section 5. You made it to the end of the second chapter. Way to go. This section has some more key fundamentals of statistics, so make sure you're paying attention. We're barely touching on z-scores right now. We'll dig much deeper into them in later chapters. Right now, you should be thinking about how to study for your first test for Chapters 1 and 2. The best way, honestly, is to practice problems. Once you've finished your Check for Understanding homework for all the sections and done the quizzes for Chapters 1 and 2, think about doing some extra problems in the Study Plan section of the Pearson course website. Just search by chapters and click on the sections you think you need help with. For now, focus on this section. You'll do great. Good luck. Welcome to the last section of Chapter 2, Section 5, Measures of Position. Let's quickly recap where we've been so far. Statistics is a study of collecting, organizing, analyzing, and interpreting data. We've discussed the collection process, selecting unbiased samples that best represent the population in question, how to decide on the nature of a study, observational versus experimental, and the different sampling techniques. We've talked about different methods of organizing and visually displaying our collected data. We discussed putting all of our entries into a frequency distribution, or one of several types of charts. Then we talked about how we could graph the data using histograms, pair-2 charts, frequency polygons, ogives, and others. And finally, we discussed calculations that numerically represent a data set with ideas like measuring the data set's measure of central tendency and variation or spread. That brings us to today's discussion. The mean and standard deviation provide a general overview of the data set, and they allow us to compare data sets with equivalent means. But how do we specify the position of a particular entry within a data set? In this section, we're going to learn how to find the quartiles of a data set, in addition to finding the interquartile range and how to represent the data set graphically using a box and whisker plot. We're also going to learn how to interpret other fractiles, such as percentiles, and how to find percentiles for a specific data entry. And finally, we're going to learn how to calculate and use the standard score or z-score of a data point. Let's get started. Fractiles are numbers that partition or divide an ordered set into equal parts, with each part having the same number of data entries. For example, the median divides an ordered data set into 2 equal parts with the same number of data entries in both parts. Quartiles approximately divide an ordered set into 4 equal parts. 3 distinct values will be key in creating these 4 parts. The first quartile, or Q1, has about 1/4 of the data falling on or below that value. The second quartile, or Q2, has about half the data falling on or below that value, which we've already interpreted as the median. And as we've already observed, the median may or may not be an actual value of the data set. And finally, the last value we need to divide a set into 4 equal parts is the third quartile, or Q3. About 3/4 of the data fall on or below this value. The following example will help illustrate this idea. Each year in the U.S., commuters waste fuel due to traffic congestion. Listed are the amounts of fuel in gallons per year that are wasted per year in the 15 largest U.S. urban areas. Find the first, second, and third quartiles of the data set. Okay, here's how we find the quartiles. Obviously, the data set needs to be put in order first, so do that here. Then we need to find the median because we know from previous work that the median divides the set into equal parts. And from what we just learned, the median is the second quartile, or Q2. So we find the median the same way we have before. Once the data set is ordered, we determine whether the data set has an even or odd number of data entries. This one has 15, an odd number. That tells us that our median will be one of the data entries. In fact, it will be one in the physical center of the list. In this case, that is 31. See how this entry separates the entries into 2 equal groups? There's an equal number below or to the left of Q2 as above or to the right of Q2. The next step is to find Q1. We are essentially doing the same thing, finding the median of the data set, only this time with only half the data set. Important point here, we do not include the median when finding the quartiles. When the original data set is an odd number, this is very clear, as in this example, but when we have an even number of original data points, Remember, the median falls between two numbers, as it is the mean or average of the two middle numbers. When there's an even number in the original data set, since the median is technically between those two middle numbers, you do include those two numbers in the calculations to either side of the median for Q1 and Q3. So in this case, it's simple because we just don't use the median. The remaining half of the data set also has an odd number, so that makes it easy to find the median of the first half or the first quartile, which is 26. When we do the same for the other side, we find that the third quartile is 35. So, after all this calculating, what does it mean? The way we interpret this is that about 1/4 of the large urban areas autocommuters waste 26 gallons of fuel or less per year. About half waste 31 gallons or less, and about 3/4 waste 35 gallons or less. Don't forget we can find values on the TI-84 too. You don't have to sort a large data set by hand. Let's do a problem with the calculator. Here's the background information. The tuition costs in thousands of dollars for 25 liberal arts colleges are listed. Use technology to find the first, second, and third quartiles. What do you observe? First, recognize from our previous encounters with the calculator that you need to enter the data into L1. You do this by pressing Stat, then selecting Edit and press Enter. Then you enter your data points, pressing Enter to progress through them. Now, to do the calculations, we press Stat, then arrow over to Calc, and press Enter when one variable stat, or one var stat, is highlighted. When you get a chance, you need to select L1 as the list in which you have data, and that may be different for different calculators. There are different processes to select the L1 as your list. You may need to press the second key and 1 to select L1. After you've done that, press Enter as many times as you need to calculate. It will eventually take you back to the main screen and say Done. Once it has done this, you can press Enter again, and when you arrow down, you can see the values for Q1, median, and Q3. This will come in very handy when you need to find these calculations in the future. Remember, your calculator is your friend. Here's what the display looks like on a couple of different types of technology. It shows us the values for Q1, Q2, or median, and Q3. Q1 is 47, median is 55, and Q3 is 58.5. What observations can we make about this data set? About 1/4 of these colleges charge tuition of $47,000 or less. About 1/2 of them charge $55,000 or less, and about 3/4 of them charge $58,500 or less. We give a special name to the range between the third and first quartile, literally Q3 minus Q1, called the interquartile range. For example, the interquartile range of the previous example's data set would be 58.5 minus 47, which would be 11.5, meaning the amount of fuel wasted by the middle portion of the data set varies by, at most, 11.5 gallons. We can also use the interquartile range to identify outliers, that is, to find any data entry that is far removed from the other entries in the data set. Here's how we do that. Find the first and third quartiles of the data set. Find the interquartile range, which we said was the difference between Q3 and Q1. Then we need to multiply the interquartile range, or the IQR, by 1.5. Then that figure is used in two different equations, one for lower outliers and one for higher outliers. To find lower outliers, subtract the result of 1.5 times the IQR from Q1. Any data entry less than that difference is an outlier. Now add 1.5 times the IQR to the Q3 figure you found. Any data entry greater than that sum is an outlier. Let's find out if there were any outliers in our previous example. Remember that the first quartile was 47, the third quartile was 58.5, and the interquartile range was 11.5. Now we multiply that number by 1.5 and get 17.25. That's the number we work with now. When we subtract 17.25 from 47, we get 29.75. There is a data entry less than that value, 19. It is an outlier. Now let's look at the greater than values. We add 17.25 to 58.5 and get 75.75. There are no data entries larger than that number, So the only outlier we have is 19. The outlier does not affect the IQR. We can visually represent quartiles using box and whisker plots. These are exploratory data analysis tools that highlight the milestones, the minimum, the maximum, and quartiles of a data set. Creating a box and whisker plot requires what we call the 5-number summary. The minimum entry, the first quartile, what we call Q1, the median, or Q2, the third quartile, or Q3, and the maximum entry. Here's how it's done. Once you have the 5-number summary, construct a horizontal scale that spans the range of the data with a little extra at the end. Plot the 5 numbers above the horizontal scale. Then draw a box above the horizontal scale from Q1 to Q3, and draw a vertical line in the box at Q2, or the median. Draw whiskers from the box to the minimum and maximum entries, extending the line so it follows the entire range of the data entries. Let's draw a box and whisker plot for the data in the previous example. The 5-number summary is given: 19, 47, 55, 58.5, and 61. In other situations, you will have to draw the initial number line. You'll want it to be the entire range of the data set plus a little at either side of the min and max values. In this case, the number line is drawn for you. So plot each of the points a little above the line at the appropriate spots. Next, draw a box completely surrounding and encased by Q1 and Q3 above and below where you place the points, so it will show above and below the line when you draw it. So your box will start with its left side at 47 and its right side at 58.5, and join at the top and bottom above and below the points. Then draw a horizontal line connecting all 5 of the points. It should run through the center of the box and extend out to either side of the box to the min and max. The left whisker represents about 1/4 of the data, so about 25% of the data entries are less than 47. The right whisker also represents about 1/4 of the data, so about 25% of the data entries are greater than 58.5. Also, the length of the left whisker is much longer than the right one. This indicates that the data set has a possible outlier to the left. In addition to quartiles, you can specify a data entry's position using percentiles and/or deciles. These are just other options for partitioning your data set. Deciles divide the data set into 10 equal parts, and percentiles divide a data set into 100 equal parts. Standardized tests are a great example of percentiles. This ogive represents the cumulative frequency distribution for SAT scores of college-bound students in a recent year. What test score represents the 90th percentile? From the ogive, you can see that the 90th percentile corresponds to a score of 1350. This means that approximately 90% of the students had a score on the SAT of 1350 or less. In fact, to find the percentile that corresponds to a specific data entry X, all we have to do is use a simple formula. The percentile of X is equal to the number of data entries less than X divided by the total number of data entries times 100, then round to the nearest whole number. For example, the tuition costs in thousands of dollars are listed. Find the percentile that corresponds to 57,000. Remember that this is in thousands of dollars, so a data entry of 44 corresponds to 44,000. We begin by ordering the data entries. We find that there are 15 entries less than 57, and the total number of entries is 25. So the percentile can be found by using the formula we just learned. So we divide the number of entries less than 57 by the total number of entries, and then to get that to a percent, we multiply that ratio by 100. We get 60%. That means the tuition cost of $57,000 corresponds to the 60th percentile, or the tuition cost of $57,000 is greater than 60% of the other tuition costs. This leads us into probably one of the most important concepts of elementary statistics, which is the standard score. A standard score, which is also called the z-score, measures the position of an entry X in the data set by the number of standard deviations it falls from the mean mu. It's a very simple calculation. Z equals the value of the data point minus the mean divided by the standard deviation. In shorthand, X minus mu divided by sigma. A z-score can be negative, positive, or 0. They can help us identify any unusual data values in a symmetric distribution. Let's do an example. The mean speed of vehicles along a stretch of highway is 56 miles per hour with a standard deviation of 4 miles per hour. You measure the speeds of 3 cars traveling along this stretch of highway as 62 miles per hour, 47 miles per hour, and 56 miles per hour. Find the z-score that corresponds to each speed. Assume the distribution of the speeds is approximately bell-shaped. Before we go, we really should make the following notes to ourselves. The mean is 56 miles per hour. The standard deviation is 4 miles per hour. And we can use the standard score formula because it's assumed that this data set has a bell-shaped distribution. The z-score that corresponds to each speed is calculated here. For the first speed, 62 miles per hour, we subtract 62 minus the mean of 56 and divide by the standard deviation of 4 miles per hour. We get 1.5. Then we do the next one. For the car traveling 47 miles per hour, we subtract 47 minus 56 divided by 4. This time we get a negative, which is fine. Turns out to be negative 2.25. Now the last, 56 miles per hour, we subtract 56 minus the mean of 56 divided by 4, and we get 0. Interesting. So what does all of this mean? 62 miles per hour had a positive number, 1.5, so it is 1.5 standard deviations above the mean. 47 miles per hour is 2.25 standard deviations below the mean because it was negative. And 56 miles per hour is equal to the mean. 47 miles per hour is unusually slow because its speed corresponds to a z-score of negative 2.25. Remember, we said that anything further than 2 standard deviations away from the mean is unusual. The table shows the mean heights and standard deviations for a population of men and a population of women. Compare the z-scores for a 6-foot-tall man and a 6-foot-tall woman. Assume the distributions of the heights are approximately bell-shaped. Okay, so the distributions of men's heights has a mean of 69.9 inches and a standard deviation of 3 inches. And the distribution of women's heights has a mean of 64.3 inches and a standard deviation of 2.6 inches. Pause the video and see if you can come up with the z-scores for a 6-foot-tall man and a 6-foot-tall woman without skipping forward to the solution. A little bit of a trick question to start with because the question is about feet and the measurements are given in inches. So we do just a quick conversion of 6 times 12 to get 72 inches equals 6 feet. Z-score for a man that is 6 feet tall is found by subtracting 72 minus the mean for men of 69.9 and dividing by the standard deviation of 3.0 inches. This gives a 6-foot man a z-score of 0.7, meaning that at that height you are less than 1 standard deviation above the mean height for men. To find the z-score for a woman with a height of 6 feet, we subtract 72 minus the mean for women of 64.3 inches and divide by 2.6. We get about 3.0. What does this tell us? The 3.0 is roughly 3 standard deviations above the mean height for women, so it is very unusual for a woman to be 6 foot tall. In other words, being 6 foot tall as a man is within a typical range because it's within 1 standard deviation of the center of the distribution. But for women being 6 foot tall, it is quite unusual as it falls 3 standard deviations above the average. Remember, anything beyond 2 standard deviations above or below the mean is considered atypical. Z-scores aren't going away, but we will be setting them aside for a little while. Okay. That's the end of this chapter. Good luck on the test. I'll talk to you in the next video.